Hello students, welcome back. Let us resume our discussion in section 1. Previously, we went through the definition of the modular order. We defined it like this. The order of A modulo m is defined as the smallest positive integer n, such that a to the nth power is congruent to 1, mod m. Now the problem is it well defined? What if we have an empty set so that we do not have minimum, that kind of thing? Thanks to this lemma, we have a rock-solid foundation. A and m are relatively prime if and only if there exists a certain integer n, a certain positive integer n, such that a to the nth power is congruent to 1 mod m. Therefore, this set here is non-empty if and only if a and m are relatively prime, and coupling with that with this well-ordering principle of Z plus, every non-empty subset of Z plus has the smallest element, the minimum. Yeah, we have the well-defined concept of the order of A modulo m if and only if A and m are relatively prime. If A and m are not relatively prime, then this set is an empty set, so we don't have minimum. So the order of A mod m is undefined. Indeed, in all these properties here, we assume A and m are relatively prime. Furthermore, let K be the order of A mod m. And then here are some of the properties we already proved. First, the divisibility property. A to the h power is congruent to 1 modulo m if and only if k divides h. And this thing is divisibility, so we call it divisibility property. And please don't forget a special case. In particular, k divides phi of m, and that's because of this Euler-Fermat theorem. Whenever a and m are relatively prime, a to the phi of m power is congruent to 1 mod m. So that's your h value in this case. So k divides phi of m. The next property we proved was this distinctness property. A to the ith power is congruent to a to the jth power mod m if and only if I and j are congruent mod k. If I take the counterpositive, then we are going to get distinctness. If a to the ith power and a to the jth power are distinct mod m, if and only if I and j are distinct mod k. And as a result, we have this important property, a special case. In particular, a to the 0 power, first power, second power, up to k minus 1 power are all distinct modulo m. And that's because, look at the powers. 0 to k minus 1, 0, 1, 2, 3 up to k minus 1. They're all distinct modulo k because of that division algorithm. One more thing actually. If you look at a to the ith power and a to the jth power mod m, we consider multiplications. A bunch of multiplications mod m. And then if you apply those multiplications with the same base, then we have the exponent rule, so we have addition of the powers, and that works addition modulo k. So there's a little bit more to it than just mod m versus mod k. Multiplication versus addition, thanks to this exponent rule. That's hidden deep down. Anyway, we went through these two properties, and now let's go to the third property. The order of a to the h power mod m turns out to be k over the GCD. The GCD of h and k. The GCD is a common denominator, common divisor, excuse me. So the denominator here divides the numerator k. So this quantity, this fraction, is actually an integer. Let's rewrite it as k over d, d for the GCD, and this is an integer, so let's name it as t. So for the purpose of the proof, let's take these renaming. And then we're going to prove that this t is indeed this t defined as k of d is indeed the order of a to the h power mod m, or the smallest positive integer n value, so that instead of a we have to put a to the h power, so that to the nth power is congruent to 1 mod m. How to prove that? Well, we'll prove it, but before starting it, let me mention a special case lest I forget it. The order of a to the h power is also k if and only if denominator is 1. So we have k over 1, so d is 1. In that case, k and t will be the same. Yeah, that's trivial. Alright, we went through everything except for the proof, so let's start the proof. But before that, I don't think we'll be using 1.3, so let's minimize that. Let's keep these two because we will be using these at some points in the proof. Alright, let's begin. We're going to do it in a multi-step. First, we'll prove that a to the h power to this thing. As a matter of fact, I'm using t, so t power is 1. You see, k over GCD, too complicated, so I'm renaming as t. So that's what we're going to do. So t belongs to this, yes. And then step 2 is the minimum. T is indeed the minimum. That's how you're going to do it. Okay, let's begin with some renaming. Let D be the GCD. Then H is S times D, as I'm highlighting in green right now. Sorry about that, I clicked the wrong key. Okay, green. And K is TD, as I'm highlighting in purple. And then GCD of S and T is 1. Let's see. Green and purple are straightforward. D is a common denominator, common divisor, excuse me. So D divides H and D divides K. So D times some integer is H, let's say that's S, and D times another integer is K, let's say that's T, so that S is H over D, T is K over D, as you see over here. But what about this? GCD is 1, S and T. Well, that's because D is a common divisor, not just common divisor, but the greatest common divisor. So all the prime factors, all the common prime factors of H and K are absorbed into D. None of them is left to go to S or T, so S of T do not share any prime factor. That's one reason to see that S and T are relatively prime. Another way to see it is to rigorously prove it using this Bezoos linear combination expression. Hx plus ky is D for some integers, x and y, and then H is S times D, right? And then K is T times D. And then right hand side is D to begin with. So dividing both sides by D, we get Sx plus Ty is 1. And that's precisely what we have here for GCD. The GCD part, the red part, will not be used in step 1, but it will be used in step 2, so remember that. So let's come back to green and purple. These are common divisors, so H can be written as SD, K can be written as TD, and in particular, K over D is T over here. Therefore, let's do A to the H to this thing. Let me expand the font a little bit so that you can read the powers better. And this thing here can be rewritten as K over GCD, so K over D. So this thing is T, do you see that? Too cumbersome. GCD is D, so K over D, A to the K over D power, A to the H power to the k of d power, excuse me, can be expressed as t power, as I'm highlighting in purple right now. And then h power here is so hard to utilize this mouse pad. H is SD, as I'm using green to emphasize. Yeah, I just use green and purple there. And then what am I doing? And change the order of this multiplication. This is basically a to the s times d times t, so you can change the order. Multiplication is commutative, so t times d first, and then to the s power. We can always redo that. Reorder the multiplication. And then what is t times d? That's k. Now a to the k power is 1. Remember, k is the order of a mod m. So we have 1 to the s power. This thing turns out to be 1. So a to the h power to the t power is indeed 1. Let's see what we want here. T. Yeah, t is the quantity we want. T is the target order of a modular m. So it must belong to this set, and it must be the smallest element. We just check that it belongs to this set. A to the t power is 1. That much we are done. That much we are done. So step 1 is complete. A to the h power to the t power is 1. Alright, next, we have to prove that this is the minimum. To prove that, let r be the minimum. And then we're going to do this observation. A to the rh power turns out to be h to the h power. Yeah, just exponent rule. So that's 1. Therefore, we can apply this divisibility property. K divides RH. Did you see that? So we just use the divisibility property. This one, which I highlighted in brown, right here. Now, K divides RH because of this divisibility property, and H here can be re-expressed as S times D, and K is T times D. Remember those? Remember the construction? I don't need this anymore. Dividing by these, we have T dividing R times S. Now, please recall T and S are relatively prime. So Euclid lemma applies. So we have T divides R. Actually, this should have been red. I just used red over there. So T divides R. Consequently, T is less than or equal to R. Wait a minute. R is supposed to be the minimum. T is a member of, oh, I should not have completely closed it, is a member of this set, but less than or equal to the minimum. Well, you cannot have strictly less, so it should be equal to the minimum, and T is indeed the minimum. And right here, for this red, I use Euclid lemma. So we proved the minimality as well. The conclusion? Yes. We proved everything. The GCD property. This is indeed the order.